Hey, good morning, ZuriHac. I hope you all had a great day yesterday, and maybe were able to work on some code or learn something. We're going to kick today off with Simon Peyton Jones. I don't really know why I should even bother introducing him, because everybody already knows Simon, one of the key designers of the Haskell language. And not only that, but sort of continued to serve as like a guiding light and a voice of reason in the Haskell community, and prolific researcher and everything, basically. So Simon, please take it away.
Okay, thank you. Thanks. Leave the microphone. Good. Well, it is my joy and privilege to be here today. Thank you so much for inviting me, Jasper, and for organizing this amazing event in this beautiful place. I even had a swim yesterday. It is lovely. The water is warm, actually. And I can't tell you how inspiring it is to come here, because I think quite a lot of you have been alive less long than Haskell. And yet, here you all are, fizzing with energy and creative ideas and with brains the size of small asteroids, thinking about functional programming in Haskell. That's very inspiring to me, because functional programming has been my, the arc of my professional life. So here you are, the cream of the Haskell community is here today. Please do me the honor of making comments and asking questions as we go. We will, I forgot to ask about our timing. We will somehow finish on time. When are we supposed to finish?
We have an hour, we can go over a bit.
Yeah, okay. An hour, maybe a little more, but so there are microphones on either side, and they have legs, so they will run swiftly towards you. But actually, even better would be you can just shout out your question. I'll repeat it so that everybody can hear. So in the latency, so we don't have long pauses while the microphone gets to you. Okay, but it would be a lot more fun like that, because otherwise I shall just an interaction is more fun than a monologue. So what are we going to do today? We're going to take a look at the innards of GHC. So presumably all of you use GHC, but I want you to gain some understanding of what's inside it. So I call it Into the Core, because we're going to look at the core language of GHC. So here's GHC's GitHub repository. So we're not looking at a lot of compiler code, but I want you to feel a little bit more confident at looking at the code you might otherwise be. So here we are. Look inside compiler. That's the subdirectory you want first. And then inside, have I gotten this right? I haven't got my glasses on. Yes, then inside GHC, right? So GHC's inside here. And then you see a whole bunch of subdirectories, C++, and core. That's the main place we're going to look. And inside core, there is, opt. Opt is the optimizer, and that's where we're going to look today. Okay, so if you've got a laptop, you can poke around in the code a bit while we go. Okay, so here we are. We're going to look at GHC's core language. What is GHC's core language? Well, the GHC version of Haskell is, of course, what Microsoft calls a rich language. And what Microsoft really means when it says rich is large, complicated, and ill-defined. And that nobody quite understands. So Haskell has, somewhat by design, grown into being a fairly complicated language, partly because we want it to be a seedbed in which lots of ideas can grow, and some will flourish and some will die out, we'll see. But it's as a result, the language itself is quite big, and the compiler is quite big. So this is GHC's, this is a figure from a paper I wrote 12 years ago, I think, and it has some lines of code measures. So in 1992, when the compiler was first built, it was of Haskell, it was about 28,000 lines. 2011, when this paper was written, it was 140,000 lines altogether, plus about 50,000 lines of runtime system. But now, Hecate very kindly did a clever something or other word county thing, and discovered that in GHC today, there is 230,000 lines of Haskell, and I'm proud to say, 160,000 lines of comments. How long is 160,000 lines of comments? Well, if you take 100 lines to a page, that's a 1,600-page book. And that's only the comments. Right? So GHC has become a big enterprise in its own right. But the fact is, the same program is alive and well 30 years later, and in fact, it's constantly being refactored and changed, and you may help. But how, in a project this big, how are we to stay sane, right? How are we to make sure that it doesn't just grow cruft and historical debt? And so this is what we're going to do. We're going to take Haskell, this big, complicated language. If you write its data type, which incidentally, the data type, this is a new thing, or sort of gradually new thing. Let's go, how do we go up? Oh, maybe if I just go back. I should do my glasses here and back again. You'll see that here there is GHC, but there is also language.haskell, and inside that is syntax, and inside that is, so this is meant to be a GHC independent abstract syntax tree for Haskell, and then it's sort of made GHC specific somewhere else. So the idea is you can take this. So this is the syntax tree that describes the thing on the left, and it has a lot of data types. I mean, there's hundreds of constructors and dozens of data types. It's a big language. So the type checker, by design, type checks that language without desugaring it, right, so that the error messages speak of the program that you wrote. And then it goes to the desugarer, and that turns it into a very tiny language, and that's where I'm going to focus today, right? So the sort of sanity then is that the very tiny language on the right here is going to say, if we can take something big and complicated and turn it into this tiny language, then in some sense, if you add something new on the left, it's merely syntactic sugar if you don't need to add anything new on the right. Okay, so then we can focus our sort of intellectual efforts on the thing on the right. Now, the thing on the left, Haskell, thing on the right, core, this typed intermediate language. So what's the difference between Haskell and core apart from size? Well, quite a few things. First, Haskell has type inference. The type checker goes to a lot of trouble to figure out the types that you meant. Whereas in core, every binder is given its type explicitly. We'll see that, right? So it's completely explicitly typed. As a result, the type checker, the type inference engine for GHC for the whole of Haskell is a very big piece of code and is quite slow. But the type checker for core is fast and it's very small, so we can be more confident that it's right. And by the same token, because the type checker for Haskell in its full glory is big and complicated, it's pretty hard to specify, and I mean specify precisely, which Haskell program will pass the type checker and which will not. But in core, it's really easy to specify that completely tightly. So, of course, we go to great efforts to specify what Haskell's type inference engine does. You know, there's lots of papers about that. But for core, we don't have lots of papers. We have one document. It's actually in the repository. Look under GHC docs. You'll find the core spec. It's what you want. And the other thing is that Haskell, in order to support type inference, makes compromises. But it turns out that in core, some of those compromises, we'll see some of them as we go, mean that core can actually be a more expressive language because it's more explicitly typed. Okay, so there's a lot of, and some of these compromises are a bit ad hoc in the source language, but that's fine because then it gets to this principled intermediate language. So the other thing about this intermediate language is it has we can type check it. Now, in some sense, we don't need to type check core because, after all, we started with a type check program, presumably. We desugared it, obviously correctly, into core, and then I did lots of optimizations, obviously correct optimizations. But it's quite helpful to be able to type check the output of this optimization pipeline, indeed at every stage, because if you screw up in any optimization, it very frequently makes a type error. Right? And if you don't have a type checker for core, and you do make a mistake in an optimization, and it gets right the way through to the code generator, and then the program runs, and then it segfaults, it's an awfully long and painful path back to the optimization pass that screwed up. Right? Whereas if the type checker, the lint, so-called lint, checks it, you get it right after that pass. It's so much better. So, let's see, yes. The other thing about having a small language, of course, is that you only have a small language to optimize and transform and reason about and do analysis on. So it's really good being small there. Okay, so far so good? This is all just out of context. Any questions, any observations? Yes, please.
Clarify, is core actually a subset?
Is core a subset of Haskell? No, it is not. Well, I suppose, You'll see. I mean, in some sense, if you look at it through half-closed eyes, yes, it is. It has Lambda, it has application. But it also has big Lambda, which isn't in Haskell yet, though it's coming. So actually, in a sense, Haskell is growing so that so that it really is a superset of core. Yeah, that's what I meant by core being a bit more expressive in some ways. Okay, anyone else? Good. Okay, now then, I think this idea of having a statically typed intermediate language is actually, as it turns out, quite unusual in production compilers. Most production compilers, they may have a type-checked source language, but then they go into an intermediate which is not statically type-checked. So in a way, for me, this is one of GHC's big intellectual experiments, is can you take a statically typed programming language and run right the way through, not quite to the bare metal. We don't go all the way to typed assembly language. That was a really interesting project called, look up the TAL, T-A-L, typed assembly language in CMU, Greg Morissette, 20 years ago. It was an amazing project. They went right the way through to statically typed assembly language. We don't do that, but we get a long way through the pipeline. Okay, good. Now, then we're going to say, so what should core actually be like, right? So obviously it's going to start with being like the Lambda calculus. But then, so this is my thought processes, along with Phil Wadler back in about 1989, 88, 89, 90 time. So clearly it was going to be, the intermediate language was going to be a Lambda calculus, but it needed to have some kind of type annotations, right? Because Haskell is a type language. And so we needed some kind of type system for core, but we didn't quite know what. So one thought was start with the Lambda calculus, just sort of sprinkle type annotations of it. The simply typed Lambda calculus wasn't good enough, right? Because Haskell is polymorphic and simple types don't permit polymorphism. But so we just thought maybe we should ad hocly, as compiler writers do, say, well, hey, how hard can it be? Let's just slap a few types on some binders and see how we go. So here's an example now. This is the compose function. Written dot in Haskell, and it has the type written at the top here. Does this sort of work? Yes, at the top here. And then it takes f, g, and x. It just applies f to g of x. But I've given a name to the intermediate here, g of x, so that I can have a local let binding. So core, in fact, has let bindings. Now, this version of compose has a monomorphic type. But suppose I want to have the polymorphic type for compose, like this, right? You'll recognize this type at the top. I'm sure you all, do a few function compositions before you have breakfast. So, but now what type is tump? Well, F has type B arrow C, and G has type A arrow B, and tump has type B. So if I'm going to put a type on every binder, I've got these A's and B's floating about. And now you begin to get that queasy feeling in your stomach as a compiler writer when you've got A's and B's floating about and you don't kind of really know what they are because they have no binding site. Right? What is A? Right? So at this point, I don't know why I didn't think of this, but Phil Wadler said to me, Simon, what you need to do is to use the second-order Lambda calculus, so the Girard's system F from Jeugt. And here's what you do. In other words, just take it off the shelf from some papers that I had previously read. I had actually read these papers, but I thought they were unbelievably esoteric, just the kind of thing that people would do so they could prove strong normalization or something. It was really so. But actually, it turned out we could directly use it. So what we do is we're going to take. Beg your pardon. So just before, let me pause for a moment to say, what the way to make the queasy feeling even more queasy is to say, if you do beta reduction, then you can see things going wrong. So here I've got compose, and I've applied it to neg, to ispos and neg up here, right? That application. If I do some beta reduction, right? So I replace the call to compose by its body. Replacing ispos, but replacing F by ispos and G by neg, well, then I get this. And now it's even more obvious that something's gone wrong, right? Because I've got this thing called tump of type B, but B is clearly of type int. Is that neg? Yes, it's of type int. Clearly gone wrong. Okay, so let's use system F, and this is what system F looks like. So many of you will know this, but maybe there are some of you who have not yet encountered big lambdas, and this is a moment that you will remember for the rest of your lives, right? When you met big lambda for the first time. So maybe you don't remember that memories in the past, that's fine. If so, here's a quick revision. We're going to put an explicit lambda for A, B, and C, so queasy feeling gone. A, B, and C are now bound. This lambda is really the same as this lambda. That's a big lambda, and the Greeks had capital letters, and this is a big one. So it binds type variables. And then, so now we've got a binding site for those three. And in an application now for compose, we don't just apply it to its value arguments, we also apply it to its type arguments. And this is what I thought was so weird when I first came across it in these papers. You've got a function that you're going to apply to a type. What does that even mean? But you just have to sort of suspend disbelief and follow the rules, and everything works out. And in fact, at runtime, these big lambdas are going to disappear, and the type applications are going to disappear. They don't happen at runtime, but they super happen at compile time. So compose, this at, is just an ordinary argument. So compose is applied to int, applied to int, applied to int, bool, applied to its pos and neg. So now if you do beta reduction, well, you just do, you got this lambda, lambda A, lambda B, lambda C. So A gets instantiated with int, B gets instantiated with int, C gets instantiated with bool, F gets instantiated with ispos, G gets instantiated with neg. Do you see that I just did the same thing for the type arguments as for the value arguments? And then we get this, and look, Trump has miraculously got the correct type int. So this was like, the sun was rising. I could see how to build an optimizer compiler, one that does a lot of beta reduction at compile time, and still make the type sort take correct. So this is a big thing. Let's just pause, make sure, is everybody happy here? Yes?
So does every function called in core have explicit type parameters?
Does every function called in core have explicit type parameters? No, only the polymorphic ones, right? So if in its type you see for all A, then every call will be that function applied to a type. If you don't see the for all A, you won't. And if you see int arrow for all A dot blah, then you'll see f applied to 3 and then int, right, a type argument, right? So it just follows the lambdas, follows the type. Yes, please.
Does that mean it was very simple to implement?
Say it louder, please.
Does that mean it was very simple to implement the explicit type annotations that we got like in ZuriHac?
Oh, yes. Was it very simple to implement the explicit type applications? Yes, so in fact, when in Haskell now, you can say f at int, right, that's why I put the ats here. That came directly from core, right? So when the gentleman over here said, is Haskell a superset of core, this because it's so useful in core, we thought, we shouldn't deny, you are Haskell users, this glorious opportunity to do type application. That's exactly where it came from, and it's why it's dead easy, yes. Yeah, yes? Oh, is this to do with higher rank types? Yes, it's higher rank types in the sense that if you can have for all anywhere, right, like certainly in argument types and so forth, then it's quite difficult for the type inference algorithm, but to stay sane, I mean, so in core, you can certainly have for alls everywhere, and when one of those for alls, so if you've got a function whose argument type is for all A, AOA, and then you say f of x equals, well, that x has type for all A, AOA, so the calls of x will indeed get a type argument in core, yes, and they can in Haskell too, yeah.
How is big lambda different from type application?
How is
big lambda different from the type application we have now?
Oh, how is big lambda different from type applications? Well, big lambda is a lambda and type applications are an application. So these guys here in core are the same as the ones in source Haskell, right? And soon you will get, because we've got an accepted proposal, we just need to implement it, soon you're going to get big lambda in source Haskell as well. So you'll be able to say lambda at sign a dot blah. And then that's the big lambda. Yes?
For inlining, what about when you're not applying a concrete type? What if you're threading through a type parameter through multi-levels of polymorphism? How does it disambiguate the name of the variable?
Ooh. I'm not sure I can pass that question. It was something to do with if you've got multiple levels of this and you plumb types deeply.
So say instead of compose at int, we're saying compose at a and inlining it, do the local names of the type.
Yeah, thank you. So I think you mean if you apply compose to types alone but not yet to values.
Yeah, to type variables. And
yeah, to type variables, that's fine. Because
with the local names.
Yeah, if you applied a compose to a type variable, well, so if this argument to compose, instead of ispos, was a variable x, a term variable x, whose type was a, right, bound presumably by some enclosing big lambda, then everything just works out. You just do ordinary beta reduction. Essentially, it works out in exactly the same way and for exactly the same reason that it works out with little lambda. So yeah, give it a try. And if you have any trouble, ask me later. But the wonder of System F is it all just works out. There are no bumps in this particular road, which is great. Anyone else?
Or be even simpler if values and types are in the same row.
Ah, yes. Such a simple sounding question. Yes. Why don't we make values and types into the same thing? Yes. And then you get dependently typed programming, and that indeed is a deep swamp. Into which I have, struggled for some time. So yes, it's a good idea. Yes, there's an enormous research literature about it, but System F at least completely cleaves types from terms. In GHC, we have terms, we have types, and types have kinds. Kinds and types are the same thing. We have not yet collapsed terms and types. Richard is trying to get me to do that, but I'm resisting. Yeah. Yes. Oh, this is a language design question. You're saying, in source Haskell, if you write a type signature with a for all A, that A scopes over the body. What if you have a lambda, a big lambda in the body as well? What's the difference? So there's really no difference. So in the proposal, go read the proposal. Essentially it says, if you're going to have the for all that scopes over the body, then you don't get the big lambdas. If you have the big lambdas, it's one or the other. But it's very confusing if you try to do both at once. The for all, the fact that a type signature, which might be far away, has a for all that scopes over some code that isn't lexically below it is always an odd thing about Haskell, right? So in a way, that's the oddity. Big lambda is the true way, right? I mean, it's a jolly useful oddity, right? I put it in there and I stand by it, but there's a little bump in the road in terms of surface language design there. Yeah. Good. Okay? All right. So where are we going to go from here? So that's so much for big lambda, right, and type applications. I just think it's worth, if you ever look at core, you will see these big lambdas and type arguments floating about, and it's helpful to feel secure about that. But the good news is that part really isn't hard in the end, which is great. So what else is in core? Well, core also, because it has algebraic data types, so the data types you declare, they're fully part of core, and therefore data constructors can appear in core terms, and also we need case expressions to analyze those data constructors, but they are flat, right? No nested patterns in core. And core also has let expressions, as we've seen. So here is the syntax of core. This is our little language, so written in sort of math speak. So an expression is a constant, a variable, an application, a lambda. A type application and a type lambda, we'll see we collapse those in the language I'll show you. A let expression or a case expression. And what's a let? These bindings can be just a non-recursive variable equals expression. I should have said x:t equals expression. Oh, look, the lambda has a type on it. And I made a mistake here. That should say x:tau. Every binder has a type on it. And let's see, what are case alternatives? They can either be default or just a literal case like 3 or a data constructor. And what are types? Well, here are types. And they're familiar, pretty familiar from source Haskell. Okay? So, pretty small language. And here is what it looks like if you look at the actual data type. So when you're looking at GHC, this is in GHC core, or GHC.core.hs. This is the module that contains it. It pretty much contains exactly this data type. Look, here's expressions, variables, literals, applications, lambdas, let, case, and type. This is for type arguments, right? So when I say f applied to int, then I'm going to use the ordinary app, but the argument is going to be wrapped in type. Does that make sense? So at one stage I thought about having type app, but it was more fun this way. Now look, this lambda is used both for term variables and for type variables. That's another design choice. We said, oh, okay, so rather than having lamb and big lamb, we're just going to have lamb, and we're going to distinguish between the two because variables, you can, are some type of term variables, IDs, and type variables, tyvars. Okay, so this is an important thing to bear in mind when you're looking at GHC, that it is a choice, right? So it's very convenient, say when you're asking for the free variables of an expression, well, it has free term variables and free type variables. It's convenient to have some type here, var, to say it's a set of vars, right? And some of those vars will be term variables and some will be type variables. Just occasionally you say, well, I've got a set of things, I know they're all type variables, and then it's a bit annoying that the type system of the compiler doesn't exclude the possibility that some of them might be IDs, but there you go. That was a choice we made. I think it was a good choice. What are cases? Well, there's a scrutiny and a bunch of alternatives. Each alternative is a triple of one of these altcon things, or I haven't shown you that, and a list of binders and a right-hand side. These altcons are distinguished between default, literal, and constructors here. Bindings are non-recursive or recursive. And do you remember I said every binder has its type here? X colon tau, and I said I missed it out here. Well, where is the type? Here. Where's the type gone? It's here, it's inside the ID. So every var has a name and its type, right? So even the occurrences have its type, yeah.
So really, it should say there var instead of ID.
Oh, here? Oh, yes, sorry. It should, yes, there's a type synonym. Type ID equals var. Yes, thank you. So this is a little, so it's not a type distinction, it's just a type synonym, but all over GHC, where I thought, this is definitely an ID, I've said, use the ID type synonym. Thanks for pointing that out. Yes? Yes. Oh, why do we need a default case in case expressions? Well, because sometimes you have big sum types, with hundreds of parameters, right? Hundreds of constructors. And in the source program, you wrote, case x of, and, a arrow, right-hand side one, underscore arrow. Now, well, I could have expanded it to hundreds of constructors, but that would blow up the program. And it works even worse if you say case x of 3 arrow something. Actually, enumerating all the integers would make GHC run really slowly. Yeah, at the back.
Is name the drawing or is it text?
Oh, what is name? Yes, another. Yes, it's in computer science talks. You can always say, what is a name? What does equality mean? And how do you handle recursion? These are good polymorphic questions. So what is this name? I'm not going to go into that very much today, but it's a string together with a unique identity. So think of it as, just being a distinct number. And what's it distinct compared with? Well, that's tricky. It would be nice to say it's always and forever distinct to all the other names anywhere in this program, but that's quite difficult to maintain. It involves generating a lot of fresh names. So in fact, we just say it just has to be well scoped, right? So the uniques are really used for fast comparison, so we don't have to compare strings, right? And also, as we see, to avoid capture, we may give something a new unique, but there is no guarantee in core, generally, that the uniques on every binder are distinct. Just that, if you've got a binder that says, I bind bind X with unique 7, then all the occurrences of X with unique 7 in that scope, unless there's an intervening one with the same unique. If there's an intervening one with the same unique, that shadows it, just like in source. Okay? So mainly the uniques are for fast comparison. We go to quite a bit of a trouble to avoid capture, as you'll see. Okay, yeah, anyone else? Right, yes.
How are coordinates?
How important is...
How are coordinates?
Oh, how is... what, did Sugar?
Coordinates.
Coercions. Yes, coercions. So I'm not going to talk about coercions at all in this talk. That's a whole... So, yes, I've left out 2 constructors. Right, 1, 2, 3, so there's 2 constructors here that I haven't told you about. I was going to show you them right at the end, because that is a whole nother hour, at least. So coercions, I thought, how hard can it be? Pretty easy to add that, but it's turned out to be a lot of work. So thank you, yeah, but I'm not going to do it today. Okay? All right, so now what does this compose? What does it look like in core? Well, it's got a lam for the A, this lambda, lam. So you could think, why don't I have a list? But we just compose them like this, lam for F, lam for G, lam for X, and then a let with a non-rec. I think it's all pretty straightforward, right? And what is this A? Well, this A, is short for, in the actual data structure, that is, of course, one of those type variables. So it's a tyvar of a name, O. It's not really a string. It's a string together with a unique, right? This little thing here. And then what is the type of a type variable? Ooh. What is the type of a type variable? Well, you're Haskell programmers. You know that type variables have types. They have kinds, right? And so in GHC, type and kinds are the same thing. So here, every ID, every term variable, has a name and a type. Every type variable has a name and a kind. What I haven't shown you on this slide is that there is a type synonym. Type kind equals type. So kinds and types really are collapsed. That, those of you who are older than 17 will remember that we had the big type in type move when we previously had kinds were previously different, kinds and types were different. Now then they got collapsed into one. Okay? So far so good? All right, so let's see. One thing I just want to mention to you, I think turned out to be a very good design choice, I think, is that in System F, as presented in theory, there are types on binders, but at the occurrences, you just say X. So you say lambda X colon int, but the occurrences of X just say X. But in GHC, every var, do you remember, every var has its type inside it. Every ID has its type inside it. So if I have a term like this one, that F there, that has a type squirreled away inside it, right? It's the same F. It's the same, little ID structure as that F there. They just point us to the same thing, right? So every occurrence site has its ID. So that means that we can write a function called exptype that takes an expression and returns its type. And here's a little part of it. Exptype of var is, well, just get the type out of the var. Remember, just so if it's an ID, get its type. If it's a type variable, get its kind, right? So if it's a lambda, well, what's the type of a lambda? It's a function type. So it must be a funti. And what's the left-hand side of the arrow? Well, the type that's on that binder. And what's the right-hand side? Well, it's a recursive call to the body. Do you see how simple it is? So exptype is a completely pure function. There's no gamma, there's no environment. You just say exptype can take an expression and give you its type. It's used all over the compiler. Right? I see it a lot. Okay. Now, I think I'm going to skip this because I think it's straightforward. This is just saying that the type checking thing, the lint stage, is just as exptype is easy, so checking that a core term is well typed is also easy and fast. I sort of mentioned that before. Okay, and one way to say this is a good mantra to repeat to yourself, before you go to bed, is that in core, the idea of an explicitly typed language is that the syntax of the term encodes its typing derivation. So if you have this lambda here, a lambda R of some body, there is only one typing rule that has lambda R on the bottom line. So as soon as you see the lambda R, you know that you must be using the fabs typing rule, and you can then say, okay, so I need to extend the environment and look at R4. And now it's an application. There's only one rule to use and so forth. So the syntax of the term, that is the stuff in red, encodes the shape of the typing derivation, that is this entire tree. And type checking amounts to just working out the typing derivation and checking that everything's consistent. Okay. This is not true of Haskell itself. Because there we got to do type inference. Okay, so this is a good pause point. Any other questions? You can read this slide at this point. This is our data type. Yes?
Every variable has its type, and that doesn't mean that it's blow up.
If every variable has its type, does that mean things can blow up, in implementation terms, just take a lot of space and time? Well, it doesn't have a copy of its type, right? Remember, the lambda has if you think about it in implementation terms, I've got a data structure, lam, and there's some variable, a little ID structure, a little subtree. That same subtree is pointed to from all the occurrences, so they're all shared, right? So you can look at it, but it's pretty much always shared. There are problems with loss of type sharing in GHC that do make things blow up, but not that one. And we're pretty careful to make sure that we always carry down with us the, as it were, master copy from the binding site and plug that in at all the occurrences, rather than, say, substituting over the type at each occurrence. That would be slow. Yeah. Okay. So now we're going to look at the optimization pipeline. So this is roughly the way GHC's pipeline works. We sort of parse the program, rename it. That deals with all the scoping issues. Type check it, desugar it into the tiny language, and then here's the simplifier that we're going to talk about a bit, and that does then there's lots of other optimizations in this pipeline as well. So do lots of optimizations here, go round and round. Then we tidy it up and then feed it back off down to the code generator, which I'm not going to talk about today. Okay, and you can see this in action. So here's a little program. If you say dedump simple, a little flag you can give to GHC, it'll show you the output of so-called tidy core. That is at this point. So after it's been type checked and desugared and optimized, then you just before it goes off to the code generator, this is what you can see. So here's this function f with type. I gave it a type signature, type int to int, and there's some stuff that the compiler's added to it. But here it is. F equals. Here's a lambda. There's its type ascription, and here's what's this? Oh crumbs. ghc.num.plus. Oh, there's a type application. Right? Remember those type arguments? But what is this? I said plus here. What is this stuff? Oh, that's the, remember this is an overloaded plus. So this is an overloaded plus has type for all A, num A, double arrow, A to A to A. So here we are. For all A, what have we got? So it's got the for all, so it must have a type argument, int, and then it's applied to what's that num A? That's the num int dictionary. I'm not going to talk so much about today, and then two value arguments, x and we'll have a look at what this iHash business is. Okay, so it's a good way of seeing core by just doing this.
Print core without the fully qualified names.
Can you print core without the fully qualified names? Yes. Desuppress module prefixes. There are a lot of, you should look at all the -d flags that let you switch off bits of printing. And by the way, all this core printing stuff, it's never had a lot of love. It's sort of, somebody whipped it up at the time, and then it's been incrementally changed. It's not a great printing format, so feel free to improve it. Now then, another thing you could do is say dshow passes. Right, and that shows you, look, there it says I'm doing the parser, renamer, desugarer, simplifier, and then I tidy, and then I feed it through core prep and STG, and so forth, and it tells you the size after every stage. That can be quite nice sometimes. This is for without optimization, right? So there's only one run of the simplifier. If you want to optimize, -O, well then, what you see, what this food turns into looks rather different, doesn't it? Look, here's foo.f, and now it's got, instead of that plus applied to the fnum dictionary and so forth, it says, oh, this is an int, and it's doing case on it and taking it apart to get an unboxed int, and then it's unboxedly adding it to one and wrapping it up again. So, this is what you get from, and there's more stuff here. I'm not going to, but if you do dshow passes with optimization, you'll see that a lot more passes take place. So it's going to be a way of getting a kind of overview of what's happening to your program. And if you say, other thing, look at all the D flags. If you say D verbose core to core, it'll show you the output, the entire output after every pass. That's quite enjoyable to look at if you have a sort of masochistic tendency. Okay. So now, I'm going to, but mainly I want to zoom in and talk a little bit about some optimizations that we do on core. Not so much analyses, just optimizations. Okay? Yep.
Type check a function. Can you use in the first step, in the first type check of the Haskell language, is it?
Right here?
Yeah.
Yeah.
Can you use the core of the values used, or do you need the Haskell of the
Oh, you mean, so if I'm compiling a module that uses functions defined in some other module, what do I need to know about the other module? Well, I need to know the types of the functions. Just the type. So, in fact, there is no difference between the Haskell type and the core type. This is another design decision that we made that says, really, there's only one notion of type. So I've got a slide. How far ahead is that slide? Oh, yes, here. So when I compile the prelude, say, through GHC, not only do I get an object file of executable code, I get this HI file, the interface file, and it contains the type signatures of all, and you don't have to ask whether there's a Haskell type signature, just the types of all the things that are exported by Prelude, right? Then when GHC is compiling module X and imports the Prelude, it goes and reads this HI file, this interface file, and now it knows the type of not and null. There you go. And it produces x.hi, little h, sorry, that's Microsoft auto-capitalizing for me, and little x, this file will give the signature of, in this case, not null, because it's a function I defined here, okay? And you can look at the contents of interface files. If you say ghc -- show iface, oh, but what is it? If you look at foo.hi, it'll look like nonsense, right? Because it's a binary format. Right, it's not an ASCII format. So this show iface flag takes an HI file, not an HS file, and it lets you see it in somewhat readable form. So here it is. This is the thing for neither of those. But it says here is I put in red some significant bits. This is the type of F, which is exported by module foo. And also here is it unfolding. We'll talk more about that in a little while, okay? And then all of this stuff here is to do with recompilation control. Has this module changed since I last compiled it? And therefore, do I need to recompile people who depend on it? There's lots of hashes and stuff to do that. Yeah, okay? All right. So where are we? Yes. Yeah, fine. Anybody, any other questions? Let's look then at some of the insides of the simplifier. So in GHC's core optimizer, it's got quite a lot of passes that do discrete things like demand analysis or specialization or float in or float out. But it has one pass called the simplifier that attempts to apply a lot of small optimizations fast. So here are some of them. We're going to look at some of them. But the idea is that these optimizations, each one individually doesn't do very much, but collectively they do a lot. So it's kind of like where they're going to cascade and do a lot together. There's a paper about this you can read. In the slides for this talk, you can follow the link, but it's on my homepage as well. So what happens inside the simplifier? Here I'm going to just go through some of the things that the simplifier does. Probably the most significant thing the simplifier does is inlining, right? That says take something from a definition site and move it to its use site. So I call it let inlining here because it basically takes, I've got a let x equals some right-hand side, and there's some occurrences of x on the right-hand side, and I'm going to take at least one of those occurrences. I don't make this decision for the let as a whole. Usually it's on a case-by-case basis. At a particular occurrence site, I'll say, shall I replace x by RHS at this point? So if RHS was a lambda, that is if x was a function, that is at least part of function inlining. It says, rather than just calling it by name, I'm going to take the whole lambda and slap it in right here. Okay? So that's a pretty simple thing to do, but if it was let x equal 3 in blah, 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 of course it makes sense to replace x by 3 at its occurrence site. Maybe I then get to say, x plus x turns into 3 plus 3, and I can simplify that, and so forth, okay? Now, we do have to be a little bit careful, because my friend over here is, essentially silently pointing out, is that if I've got let x equal y plus z and y equal 44 in x plus y, now suppose y is presumably bound somewhere out here, right? There's an enclosing let or lambda for y. This y is a different y. Right, you may say, don't the uniques keep them separate? And I'm saying it's hard to guarantee that. So we're going to say in core, it's perfectly allowable to have shadowing. It's allowable to have shadowing. The simplifier must be okay with that. So that means when I replace x by y plus z, I better not let that y get captured by that, right? That would just be wrong. Okay? So what do we do? So the simplifier goes to some trouble as it goes down, as it walks down the term, carrying, as it were, in its head. So it's going to remember that x is equal to y plus z, and when it gets down to this y, it's going to say, but it's also going to remember all of the in-scope variables. It's called the in-scope set. If you see the term in-scope set in GHC, it always means the same thing, and it's the set of variables that are in scope here. That is bound somewhere outside. So y, if it's bound outside here, presumably since this exists, y will be in the in-scope set. When we come across this y, we say, oh darn, it could be, since y is already in scope, I'd better rename this y. So on the input to the simplifier, shadowing can happen, but as the simplifier goes, it removes shadowing. So it will replace this y with y prime and add to its list of substitutions to replace y with y prime everywhere. Right? So now when it gets to this y, it will replace that y with y prime. Okay. All right, so take a bit of care. There's another paper about this that you might enjoy reading called Secrets of the GHC Inliner. Who would not want to read a paper like that? And it describes all this name capture stuff. Now, when I said let inlining is a crucial transformation that the compiler does, it's also one of the squishiest. It's subject to a lot of heuristics. So this is a place where smart PhD students and such like might make a difference, right? Because it's not easy to get this right. So what are the problems? Well, one thing is I might duplicate the code, right? So RHS is now going to maybe appear more than once. So if RHS was big, you might worry about just code bloat, right? So to address that, you might think, but if X only occurs once, that wouldn't matter, right? Then I'd just be moving it from its definition site to its single occurrence. So then you might think, well, okay, how would I know if it occurred just once? You have to do some kind of analysis, right? So in fact, every run of the simplifier is preceded by a run of the so-called Occurrence Analyzer, which you will find in ghc.co.op.occanal, and the Occurrence Analyzer is a bottom-up pass. It starts at the bottom of the program and gathers up the number of occurrences of each variable and then attaches that information to its binding site. So when the simplifier walks up afterwards, it knows, oh, this X, that's used exactly once, syntactically. Okay, and so I'm safe to substitute even a big right-hand side. Occurrence Analyzer is super important. Occurrence Analyzer also does dependency analysis. Remember I said we had letrec in the core language? The Occurrence Analyzer, because in any case it's gathering up occurrence information, it's in a position to do strongly connected component analysis, because maybe a letrec was all tangled up together but has now become untangled and you can turn it into a bunch of lets. Okay? So, another worry is that you might duplicate code. Duplicate code. Even if X occurs many times, you might think that if the right-hand side is small, we could still duplicate it. So we might want to do some size computation, and you'll find all of that size computation in ghc.core.unfold. Then you might worry about duplicating work. Right, so if X is like factorial Y, and that's nice and small, but if you replace X by factorial Y at every occurrence, you might duplicate the exercise of concurrence, of factorial, right? But if it was just a lambda, then you would duplicate no work. So maybe we need to do a little bit of scrutiny of the right-hand side of the binding to say, are you a value already? Are you a head normal form? And there's various functions like expression is head normal form, we type expression to bool. Expression is cheap, we type expression to bool, and they all live in this module. And then you might worry which of the occurrences to substitute, some or all. So I just want to point out here that there's a lot of dimensions, and a lot of auxiliary functions, and that this point is a place where there's nothing very hard and fast. Okay? Yeah.
So is there a literal number for if it happens more than 10 times?
Yes, is there a, or if it's bigger than this, do you substitute? Yes, there are literal numbers. So there are lots of magic numbers that says, if the size is bigger than 12, then don't substitute, otherwise do. And yes, these things are controlled by flags.
So the follow-up question is, if I have 12 occurrences of X,
yeah,
but X equals 5, I would want to substitute.
Oh, if you have 12 occurrences of X and X equals 5, you'd want to substitute. Yes, so you look at the size of the right-hand side. If it's small enough, we unconditionally substitute. Lots of heuristics, yes. Okay, now, we talked about, this business of let inlining does work across modules. So we talked about types in HI files. The unfoldings are also in HI files. So this null and not, even though in a different module, I can inline them here and here if they're small enough, right, in a cross-module way, because they, appear in, so the interface files, as it were, contain those let bindings. And to answer the gentleman's question over here, these are core bindings, yes. So these are the core let bindings for exported functions, if they're small enough to fit in the interface file. Yeah?
You said about occurrence occurrence analysis, but what determines if something is small or
What the question is? I've talked about occurrence analysis, but what determines if it's small enough? Well, there's this, there's this function that says, that functions in here that measure size, and then there's some magic numbers as if it's bigger than 100. Don't put it in the interface. Smaller than 100, put it in the interface file. Otherwise, don't. It's all a bit arbitrary. Make it better. Okay. Now, what? Okay. So that's let inlining. Once I've inlined the function, then I can do beta reduction. That's much easier. So now I've got, if I had an f of x, I've decided to inline f. So now f has turned into a lambda. So now I've got the application of a lambda to an argument, right? So it looks like this. Well, that's easy. Turn it into a let. Right, so beta reduction, super easy. And now we're back to a let. Shall I inline x? All of the stuff on the previous page applies. Right, so the stuff that says, shall I inline this function, all this squishy stuff here, simply springs to life again when the question is, shall I inline the argument at its occurrences in the body? It's the same thing. Okay, that's quite nice. Yeah?
How do you know which transformation to apply first?
How do I know which transformation to apply first? Well, I don't really. So what the simplifier does, I'll show you in a second, is just sort of walk down the program gathering up let bindings as it goes. And then when it comes to a function application, it's saying, shall I inline this? And then if it comes to, so it's a sort of, the simplifier is a recursive tree walk that at any particular part of the program that it's at, it just tries to apply whatever transformations it can. Don't think I'd say any. I mean, it would be a bit silly to say, I start off with my program and I think, oh, let me apply that transformation there. And then I forget all of that, start again and say, oh, I got this whole program. Shall I apply that transformation there? No, instead the simplifier walks and tries to apply lots of transformations in the same place because, of course, the place you've just made a transformation is a very promising site for another one to be exposed. Yeah. Okay. Now, 5 minutes to go. This is good, actually. We're going to need to do sort of part 2 some other time because I'm about a third of the way through. So one of the things the simplifier does, it does this let inlining, it does this beta reduction stuff, and it applies rewrite rules. So it's worth knowing about these, but this is sort of high point of leverage for people who, if you're working with GHC. So, oh dear, what?
Sorry, Simon?
Did I... I pressed the wrong
Simon,
button.
I think
Good.
we can go on for 30 more minutes if you want to. I think everyone here would be more than...
They're going to need their breakfast or something.
Yeah.
No.
But yeah, feel free to do so.
Okay, all right. I give talks about how to give talks. And one of the things I say with absolutely is you must finish on time. Because... You know that thing was the speaker, these 20-minute talks or 30-minute talks, and the speaker gets the point so when it's near the end, and then it says, well, the end is coming, says, I've just got another few slides, would that be okay? And the audience, and looks at the session chair chairs goes, and the audience is going, we want lunch, but I'm going to treat this as a special case. So I would not normally do this. Okay, so let's see, rewrite rules. So yes, so rewrite rules are pretty simple. Function applied to some arguments, and it says if I see a function, any particular function applied to arguments that match this pattern, then I'll rewrite it. So GHC has quite a lot of built-in. So no lets, no cases. This is just a function call. That's all that rewrite rules really deal with. So you've got a function call that looks like this. So here's a simple one. If you see addition, primitive integer addition applied with the second argument 0, just rewrite it. And there's a lot of built-in rules like this. This is a sort of constant folding style rule. And GHC has a lot of these, and they are collected here in this module. You can go take a look. There's a whole giant list of rewrite rules, and there's almost a little DSL to write down these rewrite rules in. Now, sometimes you want to apply some rewrite rules early in the simplifier and other ones sort of later. So there's this very simple and slightly brain-dead phasing system. So a rule can be active. The simplifier runs in phases, phase 2, phase 1, phase 0. And you can make a rule active up to a certain phase or from a certain phase onwards. Okay, so these built-in rules, they're part of the compiler source code, but if you're modifying GHC, you can certainly extend them. But you can also, as you, I'm sure, know, can rewrite rules in the source code of your Haskell program. So they look like this. You write this rules pragma, and then this says, for all k, z, and g, fold r, k, z, a build g, rewrites to gkz, the famous fold r build rule. And this is just a piece of source code. This is not built into GHC. This is part of the library. And so, in effect, this allows you as library authors to write domain-specific extensions to GHC, because GHC doesn't attempt to check that this is correct, right? It's just going to blindly follow you. If you say do this, it'll do the rewrite. It will type check it to make sure that you don't rewrite a term with one type into a term with a different type, or an ill-typed term, but it won't check that it's actually correct, right? You could say, I'd like you to rewrite x plus 3 to x, and GHC will patiently do that for you, right? Okay. So, but in order to do this, right, with a user-defined rule, we need something inside GHC that can match a template like this against the term, right? So, and that, all the matching logic is all in this module. Yeah?
What about the rewrite rules where it would match on the constraints? Would that be possible?
What about rewrite rules that can match on the constraints? I don't quite know what you mean there.
You cannot put a constraint, it's totally ignored if you put it inside of the rewrite rule, right? But if you know the particular type.
I'm going to show you something involving overloading. Maybe that would type class overloading. Maybe that will help. But you cannot say, in this little language here, you cannot say f applied to x and y rewrites if x is bigger than y. This little language here is not expressive enough to let you say that. You can say that in these guys, in the built-in rules. You can do what you like, but you're writing, you're then a compiler writer at that stage. Okay, maybe it'll become clearer in a little bit. I'm not quite, or ask me afterwards. But I wanted, as an example of what the rewrite engine can do and how GHC exploits it, I thought I'd show you the type class specializer, or a little bit about it, because when we first introduced rewrite rules, they were a very narrow case. This was really our target. We introduced the whole system so we could write this one rule. And then we discovered we could use the same system to, inside the compiler for all of this. And then we discovered we could also use it for type class specialization. So here's how. So in Haskell source code, this yellow is Haskell source code. If you write a specialized pragma, then what GHC internally generates is a specialized version of this function. So this is an overloaded function. Here's $SF is that same function specialized to int. So it can just call the int multiplication function directly, no type class overloading here. But then internally, GHC generates this rule. This is a rule that says, oh, look, it says if you see this function f, oh, what's this? Applied to the type int. There's those type arguments, right? So in a rule, you can match not only on the shape of the term arguments, but the shape of the type arguments. Applied to int and then d. What's d? Oh, that's for all quantified. So it'll match on any old d, then rewrite it to SF. So what's that saying? That's saying every time you see f applied to an int that is called at type int, and given a num-int dictionary, which I am now going to ignore, right? Because D here does not appear on the right, then just call SF. Why is it okay to ignore D? Because it's the num-int dictionary, and there is only one, right? At least there ought to be only one. If you declare a second instance of num-int somewhere else in your program, so now we've got two ways of int being a num, a member of the num class, you're in trouble with this. So this is really assuming that dictionary values are singleton types, is what it amounts to. Yeah. Does that help with your question? Yeah.
Sorry, yes, but I have another one.
Okay.
Specialized pragma, would it be a good idea to have add applications instead of giving a whole?
Oh yes, in a specialized pragma, it might be nicer to say specialize f at type int. That would be a good idea. Indeed, there's a GHC proposal for allowing something even more general in specialized pragmas. It just needs somebody to push it forward. Search in GHC proposals for specialized. Richard Eisenberg wrote the proposal. It's very simple, very nice, very general idea. Just needs somebody to execute on it. Yeah.
Can we write rewrite rules with type applications ourselves?
Oh, no, can you rewrite rules that have type applications yourself? Yes, you can. So you can write type applications in your own rules. Yeah. That should work fine, I hope. Yeah.
At this point, will we have two functions, one that's specialized and one that's not?
Will we have two functions, one that's specialized and one that's not? Yes. F is still in the blue code, the core code. We'll still have F, but there may be other calls to F that are not at type int. Or maybe we'll have some calls to F that are not a type applied to anything. So yeah, the original function stays unchanged. If it turns out in the scope of a particular module that F is not exported and all of the calls end up being rewritten to SF, then the original binding for F becomes dead code. And yes, the simplifier will discard dead code. The Occurrence Analyzer, in fact, is the dead code discarder. It finds that there's a let binding with no occurrences of F and it just drops it. That's one of the other little tasks of the Occurrence Analyzer. Yeah.
Doesn't specialize already do what the type inference does?
Does specialize do what type inference does? Well, no. If you delete this line, you still have a Haskell program and it would still run. The specialized program is entirely to do with what the optimizer does. So I feel as if I must have missed the point of your question.
But the function doesn't do anything functionally different from just calling F with...
That's right. Yes. Yes, SF does exactly the same as calling F on int. It's just it does it faster, right? Because F here takes a dictionary and reaches into the dictionary and pulls out a multiplication method and does a high order call, and this turns into like one machine instruction. So SF is faster than F, but it does precisely the same thing when it is called at type in. That's the whole idea of rewrite rules. They let you rewrite a slow, inefficient program to a fast, efficient one that does the same thing. Optimizers that rewrite your slow, inefficient program into a very fast one that does something different are generally regarded badly by the users. Yeah.
Specializing is basically, you can see it as taking a function and partially applying the type.
Yes, specialize is like saying, please partially apply. It's saying two things. Please partially apply F to int and the num-int dictionary. And secondly, at all calls to F at type int, please use this new specialized version. So it's those two things.
The question is, could you also add partial application to the term?
Could you? Oh, that's right. So maybe you're saying, could you? You can write. Yes. You could say, could you partially apply my function f to 7, make a specialized version, and then every time you see f applied to 7, that would be a perfectly sensible thing to do. That's not implemented at the moment. I don't know if you have compelling use cases, then maybe you can make the case for doing it, but it's a perfectly sensible thing to do. There's nothing really to... Type classes are just a particularly potent application. Yeah. Oh, I suppose you're right. Yes, but you can't say that in your source program. Yeah, spec constra. There's a good term to search for. Call pattern specialization that does that kind of thing, but it only does it internally. In fact, let me just show you internally before. Hold your question just a second. This is what happens if you write a specialized pragma yourself, but GHC, in fact, will look at a program that doesn't have any specialized pragmas and say, look, here is a call to F and what type is X here? X is a float. So I'm calling F at float. And here it'll say, oh, look, I'm calling F at integer. And it will say, F is an overloaded function. Bad. But I'm calling it at int and at float. So maybe I'll generate my own specialized pragmas. So in effect, GHC will generate these rewrite rules internally within a module. And it will even do that across modules. So did I say that somewhere? Yes. If you say, somewhat surprisingly, inlineable F in one module for this F, then in a client module, you can have a specialized pragma, and that will then use the unfolding that was the original source code over here and specialize it. And moreover, if you say, specialize aggressively, -f specialize aggressively, it'll just it'll generate specialized copies of this specializable function in client modules just the same way as it did here. So, and indeed some people like to use specialize aggressively, it ought to be the case that if you say specialize aggressively and make everything inlineable, that you really get essentially no type class functions remain. They've all become specialized. But you get some code bloat instead. But hey, your program should run faster. Okay? Yes?
Is it ever a bad idea to specialize?
It's what?
Is it ever a bad idea?
Is it ever a bad idea to specialize? No, it's never a bad idea to specialize except for code size, so your binaries get bigger, and possibly, your code cache is more poisoned or something. But it's that kind of thing. But really, it's a pretty good idea to specialize, yeah. But if it's a big function, that could be a lot of code you repeat. Yes?
If you say specialize aggressively and make everything inlineable, is that akin to just enabling some form of whole programming?
It's not exactly. So the question is, if you make everything specialized and inlineable and so forth, there's like a whole program optimizer. It's sort of yes. So if you the reason why do you need to say inlineable here? So that the client modules can see the unfolding of f, even if it's big. Right, here's a little one, right? So if it was a giant function, but then you might want, another alternative is to say maybe to get something akin to whole program optimization, maybe you could say expose all the unfoldings in the interface file, no matter how big they are. That's called -f expose -all -unfoldings, right? And then the interface file gets bigger, but every binding is exposed. And now you don't need to say this. You can just so you get something akin to a sort of upward propagating whole program specializer. But because of separate compilation, you might have multiple. If I've got f down here overloaded, it's imported one module here that specializes at type int, and then another module here, it might specialize it at type int as well, because it can't see this guy. Right? So you might get more code than you would want. A true whole program optimizer would look at the whole thing and say, I want just one copy of f at type int. Yeah.
Can you go back to the spec here?
This one?
Yeah, I didn't understand why we had a matching on the ASCII and constraint dictionary.
What else could we pattern match on?
I assume ASCII. So we've got for all D, num int on the previous one.
Yes.
And then on the next line we've got f at int.
Yes.
How do we say f at int at int?
So just ask, why isn't it f at int at int?
Yeah.
Oh, because f has the type for all a, so I would invite the for all a num a, right?
Yes.
So the for all corresponds to a type argument, and then the next argument is going to be the num a bit. That's the dictionary argument. So every call to f will look like f applied to a type argument, and then to a dictionary argument, and then to two numeric arguments. So here, I could have written out the x and y. I could have said for all f at int dxy is specialized f applied to x and y, but I just reduce those away. Yeah.
Sort of to piggyback on the previous question, because we gave it the num int signature for D, isn't the at int actually redundant?
Isn't what?
At int redundant. Can't it infer it based on num int for D?
Oh, well, in core, I couldn't leave this out, right? Because every application, including the ones on the left, right? And also, imagine if I did leave it out, when you're doing the matching process, remember Geugt is matching calls, right? It's going to say, I've got F applied to D. Well, that's any old D. So if it was a D of the right type, you might just about get away with it. Yes, that's right. If it was a D that definitely had this type. But this might, at a call site, that might be a big expression. So you'd have to say, does this big expression have the type numint? Right? And you could call exp_type to go from a big expression to the type of the expression, but it's just more efficient to match directly on the type here. It's sort of super cool, actually. The matcher can match types as well as terms. Okay? All right, so I think the main thing I wanted to get across here is the way that in Jeugt we're trying to compose orthogonal things. We've got this rewrite rule system, and then we're going to exploit the rewrite rule system to, the specializer exploits the rewrite rule system by saying, he's going to do that job. He's going to propagate all my specializations to the call sites. All I have to do, the specializer, is to figure out which calls to specialize, generate the specialized code, and generate the rules for them. So we're trying to sort of separate concerns here. Okay. Yeah. No, sorry, I can't hear.
Should it be actually instead of f at int d,
shouldn't really disappear where writing.
Oh, the question was, shouldn't I be passing D to SF? And no, I shouldn't, because the whole point about the specialized function is it knows that it's a type int. It's just going to do integer multiplication. It doesn't want to look at D. It just wants to emit a multiply instruction. Okay? Okay, let's, good. Back to the simplifier. So I want to cover one more topic in the remaining, now we got, what have we got, 15, 17 minutes. 17 minutes on join points. Are you ready? This is a completely different topic, but extremely cool. I would love you to leave with some notion about what join points are. So, case expressions, potent source of optimizations, right? So after you've inlined things, what often happens is you get composed case expressions. Case true of, false arrow, oh, this is easy, right? If you've got case of a known constructor, you can just choose the right alternative. That's easy enough. Oh, what happens if you've got case X, but there's an enclosing binding of X? Ooh. That's actually quite easy, isn't it? We know that X is a cons, so that's very like the case of known constructor case, right? So we can choose the E2, of course binding P to A and P's to A's. Easy enough? Yeah? So the simplifier always keeps track of, when in its in-scope set, it has the variables that are in scope, and they have inside them their unfoldings, their right-hand sides. So we remember not only is X in scope, but what X's right-hand side is. Oh, that should say A's, sorry. Okay, now look at this. Here's not null, which is a definition that applies, it's just a very simple function. And now I'm going to inline not, and I'm going to inline null. I put the definitions of not and null here. They're from the prelude. So if I inline not, I've got case, null, x's, and then the true goes to false, false goes to true. So far, that's easy, right? Now if I inline null, well, then I get this case expression. That's actually this part here. And now I've got a case expression that's scrutinizing a case expression. Ooh, what to do now? I think of that outer case expression as like a sort of crocodile that's trying to eat something. It's trying to get its teeth into a constructor. But it can't because there's a blooming case in the way. But the crocodile can duplicate itself into the two branches, like this. Look, I take this outer, the black case, the crocodile, and he gets duplicated. Here he is, the crocodile is here, and he's here. I've duplicated the crocodile into the branches of the case, and the red guy has sort of escaped to the outside. Okay? This is a super important transformation, right? The crocodile jumps inside the case expression and duplicates himself. And then you get great code, right? Case X's, if it's null, I mean, that's exactly what you want as the code for not null. You don't want to run all of this junk. You just want to do this, correct? So case of case, we want to do case of case a lot. It's fantastically important transformation. But you might worry that if these things were big, if the crocodile was big, then I'd be duplicating the crocodile, and that could lead to a lot of code bloat. That's not good. Users hate it if their compiler doesn't generate code that runs faster, it just generates code that's bigger, right? So let's not do that. So what can we do? Well, one thing we might imagine doing is just let binding them. So just make let bindings for J1 and J2. Now the crocodile is small and we can duplicate him. And now we've got J1 and J2 in these branches, right? That's good. Now what can we do? Well, this is case of known constructor, right? And here's another case of known constructor. That was why case of case was good, by the way, is because the crocodile got his teeth into a constructor. So we can simplify these two, and we get to here. Now the occurrence analyzer, the next time around, the occurrence analyzer will look at this and say, J1, he only occurs once. We'll surely inline him. J2, he only occurs once. Inline him too. So then we get back to the code that we originally wanted, right? But we got there without having risked in the middle this big duplication. Good? So that's the idea of join points. So we call them join points because you can think of that at this point, you could imagine that if I was executing code for this, what would I do? I do this case, and here I just jump to J1. No, so it's like in an imperative language compiler, you would say, I've got, did I have a picture of this? Yes, something like this. In a C compiler, you say, I'm going to print something, and then I got an if, and then I do some stuff and some other stuff, and then I print yes. At the end of the stuff and the other stuff, I'm going to jump to print yes. I'm not going to duplicate print yes into, stuff and other stuff. I'm just going to jump to it because it's a sort of shared join point in the control flow graph. So we've just turned what would be a shared join point in the control flow graph into a let binding. Now, I've generalized this a bit here because I skipped over something. So here's a slight variant in which instead of true and false here, I've got a maybe type, right? So the crocodile here has a just X. So now how can I play this game? Because after all, here when I let bound them, I just took the expressions and I let bound them just as they are. But here, I can't just take big 1 and let binding without doing something because big 1 mentions X. But that's fine, I can just give J1 a parameter. So J1 is just a lambda, right? Lambda calculus is great, isn't it? Right? So J1 is lambda, and then I can do exactly the same thing. No, so it all generalizes beautifully to fully general join points here, right? And then so the last component is when we come to generate code for all this, we really are going to spot these join points. We're going to treat them like lets almost all the time, but at the code generator, we're going to say, aha, that let, I don't need to allocate a closure for it, or, it looks like a lambda. That would usually mean I'd have to heap allocate a function closure and pass it around and capture its free variables and whatnot. No. I can say, oh, look, that let binding, this J here, J1, is only called as a tail call. And moreover, it's always exactly saturated. So these exactly saturated tail-called only let bindings, these are the things we call join points, and the code generator is super good at those, right? It just turns them into adjust the stack pointer and jump, 2 instructions to invoke J1. Oh, having put X in the right register. So it's really nice and efficient. Okay, let's see. Now, you have to be a little bit careful. Oh, actually, I think am I going to skip? No, I'm not going to skip this. This is important. So once you introduce join points, then you need to handle them pervasively. Look at this. Here is a outer crocodile, the black guy, who's scrutinizing this let guy here. And the let guy already contains a join point for some earlier stuff. Okay? Now, what does the crocodile do? Just do it. Just mindlessly do exactly what we did before, right? So we're going to take R1 and we're going to take. What have I done here? Sorry. Here I'm just ignoring the fact that R1 and R2 might be big, right? Let's imagine they're small, so we don't introduce new join points for the outer crocodile. We're just going to duplicate case true to R1 and to R2 into the case branches. So here we go. We push it inside this let and then inside the case, and now we scrutinize this J. So now there's the 2 copies of the crocodile. Okay? Now what's wrong with this? Oh, I should have had this slide without the crib on it. What's wrong with this? J is no longer a join point. Look, he's not tail called anymore. And worse, this R1, R2, well, the hope was the crocodile was going to find some constructors to scrutinize. But he doesn't. He's now scrutinizing a call to a join point. Well, not join point anymore. So not only has moving the crocodile in not helped very much, it might have helped here, but it hasn't helped at all here. But also, this J can no longer be compiled in this super efficient way. Now it gets an inefficient function closure. It's still correct, it'll still run, but it's not efficient anymore. So what can we do? Okay, this is the last idea I'm going to show you today. What can we do? In moving from here to here, I want to do something a bit cleverer when I'm sort of pushing the crocodile down. Inlines. Oh, inline JX. Oh, no, I don't want to inline JX because here J only occurs once. But I want you to imagine that JX's right-hand side is big. E1 is big, and J occurs many times. So I don't want to inline it. If I'd inline it, then I didn't need a join point. No, I knew something.
Put KS inside J.
Put the case inside J. Yes, yes, yes. Look at that. When we push this outer crocodile inside, we're going to push him into the right-hand side of J. J, remember, is what happens afterwards. Remember, that's what join points are. It's what's going to happen next. And this case is scrutinizing. This case is what's going to happen next, so it's going to scrutinize. So we push the crocodile into the right-hand side of J, and he still scrutinizes, that should say... that's why. We're going to make him scrutinize E2 there. But here, instead of when the crocodile comes in and meets that J, we're going to say, it's okay, that J, we've already pushed the crocodile into his right-hand side, so we can simply forget about wrapping the crocodile around the call to J. Right? So instead of wrapping it around the call to J, we pushed it into J's right-hand side. Do you see how clever that is? These join points really are like what happens next. Yes? No, does it need to know if it's a join point, or can it do it for every let binding? It totally needs to know that it's a join point, yes. So, because it's just not sound for any let binding. Can't push crocodiles into every let right-hand side. That would just be wrong, right? Baby rabbits would be eaten. No. So somehow I'm clearly sweeping something a little bit under the carpet. I'm saying it's like a let binding, and then I'm saying, but we're going to treat it specially. So we could have two kinds of binding, let bindings and join bindings. In fact, in GHC, every ID comes with a little Boolean flag that says, am I join binding? Right? And the Occurrence Analyzer sets that flag because it precisely determines, remember, that Occurrence Analyzer, it's a bottom-up traversal that sees how things occur. And it can say, this guy, he's a join binder, right? And he tags him as such. And then the simplifier can say, I know that you're a join binder, so I treat you specially in this way. So we're a little bit schizophrenic because for many purposes, join bindings are exactly like lets, right? For the strictness analyzer treats a let J just like it treats a let F. It's just this crocodile stuff that doesn't. Yes?
When you're about to push it inside of the J, you can create a new J prime in which you push it into that one. And then if you have other uses of J, just leave them be. In this particular case where you're trying to push it into, create another J.
So the question is, do we need to create a different J when we're pushing it into the right-hand side? So the answer is actually we don't, because we know that since J is tail-called, the crocodile is going to find all of those tail calls. So in fact, this new J does have a different type. So it is kind of morally a different J, but the old J is going to be dead and gone, in fact. Maybe you can ask me afterwards. I think I'm not quite sure I'm getting the full point of your question. I think you do. Right, so have a go and show me. If you think you can get away without knowing that it's a join point, then I'd be very interested, but I don't think so. Okay. So this is the paper to read. This is one of the papers that I've been involved in that has made me happiest, because it started with what seemed to be a very esoteric conversation with Zina Areola about why we don't use the sequent calculus instead of System F as GHC's intermediate language. And we went around the houses and did a 2-year research collaboration that finally ended up in this paper. I think you would like it if you read it. So it's and it's deeply and pervasively used in GHC now. You see join points all over the place. But what's nice is that we didn't actually need to change core at all, except for this bit, somewhat ephemeral bit. Okay, enough. I'm going to wrap up at this point. Yes, I'm going to pretty much finish at this point. At this point, there was a ton of stuff I haven't had time to talk to you about. Which there are people here like Sebastian Graf. Where are you, Sebastian? He knows all about the strictness analyzer and CPR analysis, and then case liberation. I'm not sure the specializer we talked about, and spec constru talked to Andreas, and float in and float out and common sub-expressions. A lot of other transformations. These are what I call point transformations. These are they work over the whole of core. Remember, adding a new transformation that works over core is core only has these small number of constructors. to write a new transformation might only be a few hundred lines of code, and then you can just add that to GHC's core pipeline as a plugin. But I haven't told you about any of these, and nor have I told you, in response to your question earlier, right, about casts and coercions and roles and new types, and all of that somehow lives in the type system of core and these 2 extra constructors. But I think I will. I think I have to leave it with lots of things that I haven't told you. I'd be happy to talk to. I'm going to be around all of the rest of today and a little bit tomorrow morning. I'd be very happy to talk to any of you who want to talk about any of the stuff that we've discussed. And do have a look in the code for GHC. I mean, in fact, I have, I had a whole series of slides that we're not going to get to about, all of the things that need doing in GHC and, how we need your help. So I really would like you to roll up your sleeves and join in. And maybe I should leave this as being the URL for GHC and talk to Ben Gamari and Matthew. Where are you? Matthew Pickering is over there. Actually, I'm going to leave the picture here, yes. Matthew and Ben, the co-supreme beings of GHC. Brian Richter, who's not here today, our new DevOps manager, and... Brian, there, right. Brian, you look completely different. Yeah, what happened? This is the only picture I could find. But it looks sort of aspirational. It has a sort of, pioneer. I'm looking at the Rocky Mountains and I'm going to conquer them. Okay.
Thank you very much. Let's have a round.
Thank you.
So, given that we have sort of overstepped our time budget, I want to ask if there are any burning questions. Good. Now, since there was a round of questions before anyway, so I guess that's okay. You're going to be here today, so
yeah, all of today. So I'm totally available. Yeah, I have no plans.
Cool.
Except swimming.
Great. So questions during swimming, and so the food trucks are now there, so we can start having lunch now. Something important, since there are only 2, let's not queue up at the same time. So they'll be here until 3 today, so everyone can just come whenever there's no line. That's announcement number 1 from my side. And announcement number 2 is, when I came in today, the cleaning lady wanted to have a little talk with me, and this is always dangerous because she has the keys to everyone's offices, and she said that we have to be a bit more careful about recycling. This is not your fault because everything's written in German, so I'm just gonna just gonna say this. So there are garbage in Switzerland is organized in sort of some categories. So there's PET, so mineral water and all these things. You crush them and you put them in the blue container. Blue, yes. Then there's glass, that's separate. Then there's carton, and that's separate. And then everything that's not in these 3 categories. Have I missed something? Aluminum as well. Aluminum cans is a separate category as well. Yeah. So aluminum, carton, PET, and carton. Carton is cardboard. Yeah. So carton is cardboard that's not dirty with things. So there are these these categories, and everything that doesn't fall in this category goes into the black bag. So that's everything else. So thank you very much for keeping this in mind. So that's announcement number 2. Announcement number 3 is that, so for the beginners track, since it should have started 2 minutes ago, but I need some time to calm down from this talk as well. So let's start at 11:45 then. Thank you very much. Thank you again.
Great. Okay, thanks.